Welcome back. We now have all the tools we need to do some of the most interesting and fascinating physics that came out of the 20th century. We've developed the idea of space and time and about how particles and observers travel through space and time, and we've developed a formalism to help us understand how those quantities work. Last time we talked about velocity and acceleration, and we remember those from our kinematic days in physics last year, but we also remember from last year that velocity and acceleration weren't really the most inherently fundamental objects. In fact, when it got to fundamental objects in conservation laws, we remember that the most interesting or the most fundamental objects that we have were things like energy and momentum. And so today what we're going to do is we're going to find out where energy and momentum live in this four-dimensional world. In fact, if you start counting things, we know that all of the conservation laws we learned about last year, the conservation of momentum was really three expressions, right? Momentum was conserved in the x, y, and z directions, and energy was conserved, for a total of 4 conservation laws. Ever since Newton's time, or perhaps even before, we also knew that this concept of momentum was in fact inherently more important than any of the kinematic constructs we have. Even when Newton wrote down F equals ma, it was first written down in terms of the change in momentum, not the change in velocity, right? And so momentum is this important quantity, right? It's one of it and energy are basically conserved everywhere, and it's been one of these quantities that we've studied in physics with such interest for hundreds of years. So in four-dimensional ideas, we can take those 3 spatial momenta and energy and combine them into one structure. And that structure is the thing we're going to call the four-momentum, where the time component contains the information about the energy of a particle or an observer, and the spatial components incorporate the information about the spatial momentum. And I've written it down here in the units that we normally use. We think about the time component as being energy divided by the speed of light. That's basically to get the units correct between the time part and the space part, and then the space part is the four momentum. And so in just looking at this construct, we can already start to interpret a particle or an observer's energy as a measure of how much momentum one has through time. Right? And that's a really cool way of thinking about it, but it also exposes this fundamental idea that traveling through time is merely traveling through another dimension, and therefore energy is really an extension of our ideas of four momentum. Right? So to change energy, you have to do work, right? And to change momentum, you have to have a force. And so there's this unified picture of 3 spatial dimensions plus 1 time dimension. But to really use it, I actually now have to think about, well, how do I assign these quantities for different types of particles? For the most part, we're going to be dealing with particles that have mass, right? So electrons and spaceships and all of these things are things that have mass and therefore travel at speeds less than the speed of light. And now I can tie the idea of the four momentum, the idea of the energy and momentum of a particle, directly to my idea of a four velocity. If I take the four velocity and multiply it by the mass, I get 2 different expressions. I get m gamma c, which is the time component of the four momentum. That's the particle's energy. And I get m gamma v, which is the spatial component of the four momentum, which is the thing that we probably use to call the momentum. To tie that in, or to convince ourselves that that interpretation is consistent, we can actually look at these 2 different terms and see if it makes sense in the non-relativistic limit. So first, let's try to calculate the energy of this particle. Well, the time component is E over c, and so E is equal to the time component times c, which is just m gamma c squared. Right now, your feeling of adrenaline of seeing this m and c squared in the same formula is flowing right now, because this was one of the things that you wanted to learn since the first day that you enrolled in a physics class. This m gamma c squared is true at any velocity because gamma can be anything from 1 to infinity, but at low speeds, right, when gamma is approximately equal to 1, I can do a Taylor expansion of gamma, which is in the lower left-hand corner here. And when I do that Taylor expansion, I see that I get mc squared when the velocity is equal to 0, right? And so the energy of a particle is given by mc squared, right, which you sometimes call the sort of the mass energy. Einstein's famous formula, right? This is physics, right? That there's energy contained in the mass of the particle somehow. And if speeds are still small, I can Taylor expand the rest of gamma, and I can get that the correction to the energy is the rest energy plus the leading term, which is 1/2 mv squared, which is, of course, the kinetic energy that you used to think about, right? So I recover this idea of energy as being the mass energy plus the kinetic energy in the non-relativistic limit. And that just ties our intuition together that this energy of the particle is a combination of sort of its mass energy plus its kinetic energy. At high speeds, though, it's not possible to do this Taylor expansion, and therefore we have to start to think about the idea of energy as being something that's that's bigger than the ideas of the separated mass energy and kinetic energy. And in fact, if you think back to maybe some of the applications that you've seen in particle physics in your life, if you think about radiation therapies that you may have heard about, or detections of particles at the Large Hadron Collider, oftentimes we talk about the energy of the particle is this, and we've dropped the word kinetic or mass because at these very high energies, when I don't really trust the Taylor expansion, I really just have one energy that belongs to the particle. And so the time component of the form momentum always corresponds to that energy, right? And it's in the non-relativistic limit that I can make this approximation, where it's the mass energy plus the kinetic energy. Well, what about the spatial momentum? Well, I know that the spatial components of the form momentum are m gamma v. Well, obviously in the v equals 0 limit, this is just m times v. That's our good old-fashioned momentum. If I again do the Taylor expansion, I get the old-fashioned momentum plus some correction factor that goes like v cubed, right? And this is actually something that if you go to really high energies is the first thing that the first correction that you see, and it's something we didn't talk about in first year physics because as far as momentum was concerned, we were really happy with just the first term in the Taylor expansion. Okay, so just by multiplying the 4 velocity times m, I've already recovered an expression for the time component of the form momentum, which is exactly what I expect from the energy formula, and a spatial component of the form momentum, which is what I expect from my intuition about momentum. Now, of course, all of this breaks down if my particle doesn't have a mass. And so we have a special case now where we have to think about particles that are massless. And I'm pretty much going to restrict myself to photons here, right? This is the particle that has no mass that we come into contact with every day. But I want to remember some things that I know about photons, which we really learned about just a couple of weeks ago. If I have a photon, I know what its energy is, right? Because of studies of the photoelectric effect, that it's proportional to the frequency, and that constant of proportionality is say h bar, and therefore I can rewrite hf as hc over lambda. At the same time, I also know what the momentum of a photon is. It's just h over lambda. And so when I think about these two quantities, the energy of a photon and the momentum of the photon, they really start to look like each other, except they're in different units, right? And so if I were to divide this by c, I actually get that E over c for a photon is equal to the magnitude of its momentum, right? So the time part of the form momentum of a photon is equal to the magnitude of the spatial part of the form momentum of a photon. If I go to this simplified picture where I allow it to only propagate in the x direction, then I can write it explicitly in terms of components. But I always know that in this photon, which I've learned from studying light, right, is that the magnitude of the time component of the form momentum of a photon is equal to the magnitude of the spatial component of the form momentum, right? And so in this case, it's going in the x direction, so I've put it all in the x component. There can be sines and cosines that mess this up, but that relationship is always going to be true because that's what we know about photons, right? We can't write it in terms of m, obviously, photons don't have an m, but I can still write down the form momentum because I know what its energy and I know what its momentum are. And this is also really interesting because we've always thought about building the momentum up from the velocity. Whereas at the same time, we also knew that things that don't have mass also have momentum. And this idea of four momentum really bridges that by rewriting it in terms of the energy and the spatial momentum. And since we know this relationship is true, that the magnitude of the time part and the magnitude of the space part have to be equal to each other, I also find out that the four dot product of the spatial of the photon momentum with itself is equal to 0, meaning that the four momentum of a photon is actually null, right? That it is perpendicular to itself, that it has no length, right? And then that gets back to this definition of in the, say, the space-time interval, right? When I get an interval, when I get an inner product that's equal to 0, I call it null, or I call it light-like, because massless particles have a four momentum whose magnitude is equal to 0. And once I have that, once I have these two different expressions, one for massive particles, one for massless particles, I can now do everything that I want to with collisions because I have my conservation laws. Momentum is conserved. Four momentum is conserved. And the statement that four momentum is conserved is the relativistic statement that energy is conserved in a relativistic way, and that spatial momentum is conserved also in a relativistic way. And so when I do conservation of four momentum, I end up with four different equations: the time component, the x component, the y component, and the z component. And I get algebraic expressions that relate the initial momentum of the problem to the final momentum of the problem. Okay, so here's your take-home message. You want to build a four momentum? First you ask yourself, is it a massive particle or a massless particle? If it's a massive particle, I can just write it as m times the four velocity, or the expression that we had a couple of slides ago. If it's a photon, if it's a massless particle, then I know that the magnitude of the time component is equal to the magnitude of the spatial component, which we usually just call E over c, because I can get either the wavelength or the frequency if I know what the energy is. And that in all cases, fundamentally speaking, without exception, four momentum is conserved.